Assalamualaikum and hi, my name is Aisha binti Suhaimi and my matrix number is 2311515551.
Good day everyone, my name is Esther Roshni Woman and my metric number is 2311515558.
Salana Sejahtera, I am Koizi Haq and my metric number is 2311551570.
Hi, my name is Nur Afika Aya and my matrix number is 23115159.
We are from Group 5 and today we are going to present about the assignment for Bode plot and Nyquist plot. For question 1A, we need to estimate the values for resonant peak magnitude and frequency, bandwidth, and cutoff rate for the Bode plot shown in the figure 1.1. We know that the resonant peak magnitude and frequency are the value from the highest point. Therefore, we can simply draw a straight line from the highest point in the magnitude plot of the Bode diagram to its x and y axis to get the values, where resonant magnitude equal to 7 dB and resonant frequency equal to 9.5 radian per second. To find the bandwidth, we can draw a straight line at -3 dB from the initial point until touching the plot and draw the line down to x-axis, then we will get the bandwidth equal to 50 dB. To find the cutoff rate, we can add up the gain at the highest and lowest point, which are -7 and -14, so we can estimate that the cutoff rate is equal to -40 dB. For question 1B, the question given a system GS and asks us to draw a Bode diagram. Before we start drawing the Bode diagram, we need to normalize the transfer function given. After the process of normalization, we found that the system had 4 components, which are gain equal to 1, simple 0 with corner frequency of 15 radian per second, pole at origin, and complex pole with corner frequency at 10 radian per second. And we need to convert the gain into dB unit, so by using the formula of 20 log K, we will get that the gain in dB is 0. So now we can start drawing the Bode plot with the gain first, which is equal to 0 for Bode magnitude and phase plot. Next, we draw for pole at origin. For magnitude plot, the line start at 0.1 radian per second at 20 dB and decrease 20 dB for each decade. For example, at 1 radian per second, the line will be at 0 dB, and for 10 radian per second, the line will be at -20 dB. And for phase plot, the plot at origin is always a straight line at -90 degree. Then we draw for simple 0 with corner frequency at 15 radian per second. For magnitude plot, we draw a straight line from 0 dB until the corner frequency and moving up until 20 dB for the next decade. Well, for phase plot, it will be a 45 degree at the corner frequency, and a decade before it is 0 degree, and a decade after it is 90 degree, and will become constant at 90 degrees. For complex pole, it is almost the same with the simple 0, just it will moving downward to negative half, and the values for magnitude and phase will be double, which are -14 dB and -19 degrees. By adding up all the values at each corner frequency, then we will get the final plot as this. To find the gain margin, we can draw a straight line from -118 degree in the phase plot until touching the final plot, and moving upward until touching the final plot for magnitude. The difference between the intersection point in the magnitude plot with 0 dB is the gain margin. Well, for phase margin, we can draw a straight line from 0 dB in the magnitude plot until touching the final plot, and moving downward until touching the final plot for phase. And the difference between intersection point in phase plot with -118 degree is the phase margin. For question 1C, the question asks us to estimate the system stability based on the Bode plot drawn previously. From the Bode plot, we can estimate that the gain margin equal to 25 dB and phase margin equal to 90 degree. Both are in positive values, therefore the system is stable. For question 1D, the gain K is increased by 20 dB. It means that our plot will be moved up by 20, so we will get the plot for K20 like this. And from the sketching, we can estimate that the gain margin is equal to 15 dB and phase margin is equal to 10 degrees. Both are still in positive value, therefore it is stable, but the stability is lower if compared to the system with K equal to 1 due to the reduction of the value for gain and phase margin.
Hi, so I'm in charge of question 2, so for the system that's given, I will be drawing a Bode diagram for K equals to 4 and also later on enable the gain and phase margin. So with the K that was given, K equals to 4, we will be substituting it into our transfer function. So once after substituting, as you can see on my solution over here, we got to know that K is equals to 1.6. Now, with K equals to 1.6, we'll be substituting it to the equation 20 log 1.6 to find the gain in dB. So we got 4.08 dB, and then for pole at origin, we'll know that it's S, and for simple 0, it's 1 over T. So 1 over 0.1 is equals to 10, and for our quadratic pole, it's 7 squared is equals to 25, so the square root of 25 is equals to 5. So from the values that we have gotten for our gain, pole at origin, simple 0, and also quadratic pole, now we can plot them on our Bode diagram. So first, let's look at the magnitude part. For gain K is equals to 4.08, we'll be drawing a straight line across 4.08 dB. Next, pole at origin is going to decrease -20 dB per decade. So the first value is starting at 0.1, which hits 20 dB, and the next corner frequency, which is 1, it will hit 0 dB and gradually decreases -20 dB per decade. So next is simple 0. Our simple 0, the value that we got for simple 0 was 10, the corner frequency, right? So at 10, it begins at 0, and then the next corner frequency, the next decade, which is 100, will be at 20 dB, and the next decade, 1000 will be at 40 dB, which means it increases 20 dB per decade. And finally, for our quadratic pole, the corner frequency given was 5. That is what we calculated, right? So corner frequency 5 will begin at 0, but then for quadratic pole, the slope is going to go times 2 compared to our simple 0, which means next value, the next corner frequency 50 will be at -40, and 500 will be at -80. Let's now look at the phase part for our Bode diagram. So first, we will be plotting for our gain. Gain 4.08 will be a straight line, horizontal straight line at 0 degrees, and then for pole at origin, we'll be drawing a horizontal line across -90 degrees. For simple 0 and quadratic pole, we'll be only using 3 values, which is the value before and after the corner frequency. So for simple 0, the corner frequency is 10, right? So we're using the value before, which is 1, and after, which is 100 for plotting on our phase part. So for our simple 0, the value 10 will be plotted at 45, the value that comes after will be plotted at 90, and the before at 0. So whatever value after these 3 corner frequencies will be a straight line. Whereas for quadratic pole, as we all know, it will be times 2 of what we had before, right? So for quadratic pole, the first value is 5. So the before value is 0.5, and the value after is 50. Okay, right? So 0.5 will be plotted at 0, 5 will be plotted at -90 times 2 of what we did earlier, and then 50 will be plotted at -180. The values that come after will be both straight lines. Now we can finally draw a Bode plot. So how do we do it? So at each and every corner frequency, we're going to add up the values and plot over there. So for example, at 0.1, if you look, we have 0, 4.08, and 20 dB, right? We'll plus all 3 of these values, and then the final value will plot it up there, which is 24.08. And then we'll be doing exactly the same step. We'll be repeating the same step for other corner frequencies as well, and then match the Bode plot, draw the Bode plot. So not only that, we can also find the slope for each differences between the Bode plot. So for example, from 0.1 to 0.5, we have 3 different graphs, right? So we have simple 0 gain and also pole at origin. The gain is 0, simple 0 is 0, whereas our pole at origin is -20 dB per decade, right? So adding all 3 of it, we get -20 dB per decade, and that's the slope for that particular part. And we have to find the slope for the consecutive corner frequencies as well. So for phase, it's the same also. We'll be adding up the degrees at each and every corner frequencies, and then finding the slope as well. So that's how we'll be drawing the Bode plot for it as well. So for part B of our question 2, we will be evaluating the stability of the closed loop system. Number 2, we'll be finding the values of bandwidth and cutoff rate of the system. And finally, we will find the stability of the system if K is increased by 30 dB. From the plot over here, we can actually see how I found the phase margin and gain margin margin from our Bode diagram. So at the negative 180 degrees of our face part, we have to draw a straight line until it reaches the face graph, right? At the intersection, we're going to find for the intersection at our magnitude part, and then that's where we are getting our value. Same goes to our, that's the value for our gain margin. Whereas for face margin, we'll be looking at the 0 dB of our magnitude part, and then the intersection on the magnitude plot, and the intersection at our face plot, and finally we'll be getting the value for our face margin. So for the intersection earlier, we got to know that the value for gain margin was negative 36 and face margin was negative 180. So these two values will be substituted into the formula where for gain margin 0 minus negative 36, finally we got 36 dB, and for face margin it is negative 135 minus negative 180, we got 45 degrees. So since both gain margin and face margin are positive, the system is said to be stable. To find the bandwidth of the system, I actually used the formula that was given on our lecture slide. So on this formula, we were required to find the value of Wn and also the damping ratio. Wn you already knew, damping ratio I just had to substitute the value into the equation given. So once after getting the values, we're just going to substitute back into the equation, and finally I got 4.35 hertz. The bandwidth is 4.35 hertz, and cutoff rate of the system is also known as the final slope. So final slope, how do we find final slope? Final slope is the slope of each and every graph that we drew earlier. So simple 0 has a slope of 20, gain has a slope of 0, our quadratic 1 has a slope of negative 40, and pole at origin has a slope of negative 20. So adding all of these, we get negative 40 dB per decade. So that's our cutoff rate. So on this part of the question, we're looking for the stability of the system when a gain of k equals to 30 dB is added. So what we do is that first of all, we have to draw a new Bode plot on the Bode diagram. So how do we do that is at the previous Bode plot, we're adding 30 dB, and then we're plotting a new Bode plot. So once after plotting the Bode plot, we will follow back the same method to find the gain and face margin only. So from the graph, we got negative 6 for gain and negative 180 for face. So substituting it into the formula 0 minus negative 6, we get 6 dB for our gain margin, whereas negative 170 minus negative 180, we get 10 degrees for our face margin. So from here, we get to know that yes, both gain margin and face margin remain to be positive. So the system is actually stable, but then the stability of the system is said to be reduced significantly because of how small the value has gotten.
So for my part, I'll be explaining for the question 4. The Nyquist diagrams of the control system in ventilators are shown in figure 3.1. So first question is determine which system has a good stability. Justify your answer. So based on the graph here, from the plot of Nyquist, we have two systems, which is system 1 and system 2. We can see from the graph, the system 2 has a good stability because the Nyquist plot does not encircle the critical point, which is the negative 1 plus J0, and has a larger gain margin and face margin. And for question 4a2, we have to determine the number of integrators in S1 and S2. Justify your answer. So from the previous graph here, we can see the system 1 S1 starts at finite point, which shows that it has 0 integrators, while the system 2 starts from infinity in vertical direction, which shows that it has 1 integrators. So for question 4b, the transfer function of an enlargement mechanical habitation system is given as GH equals to k over S squared plus 2S plus 5. So if k equals to 10, draw the Nyquist plot for omega equals to 10, 0 to omega equals to infinity. So we list out our equation first, and then we substitute the k equals to 10 into the equation, and then we have the first step is we have to set S equals to j omega, and then we substitute into our equation, and then we have to list out magnitude equation where we have to take out the j from the equation, and then for the phase equation we just have to do phase equals to tangent imaginary over real, and then after that we have to set omega equals to 0, where we substitute 0 into the magnitude equation, and there we get 2, and then for the phase we substitute 0 into the phase equation, and then we get 0 degree for the equation. And then for S equals, and then we have to set omega equals to infinity. We substitute into the magnitude equation, and then we got 0 there. And then we substitute infinity into the phase equation where we got negative 180 for the phase. After that, we do rationalize and set imaginary equals to 0 to get the real axis crossing. We take the equation, we times with the conjugate where we take the denominator, change the sign, and times with it. And then we do the simplification until we get the simplified equation. After that, we take out the imaginary part equals to 0 where we have to find the values for the omega. Here, first we take the negative 20 omega equals to 0. We do calculation, omega will become 0. And then we take 5 minus omega squared equals to 0. And then we do calculation, and then the omega will be sub 5. And then it is a positive frequency where the omega p equals to 0 and sub 5. After that, we do substitution into the equation where we take omega equals to sub 5 and then substitute into the equation, and then we'll be getting omega pi I equals to 0 radian per second. After that, we take the omega pi I equals to 0 radian per second, we substitute into the equation Lj omega, and then we'll be getting infinity. After that, we can do the plotting for the Nyquist plot. So for question 4c, evaluate the closed loop system stability based on the Nyquist plot in B and justify your argument in terms of the closed loop gain margin and phase margin. So from the graph we sketched before, the Nyquist plot does not encircle the critical point, which is negative 1 plus J0, and closed loop system have no right half pole. So from here we can see the closed loop is stable, and then the gain margin and phase margin are positive. So lastly, for question 4d, we have to evaluate the stability of the closed loop system if an integrator is added to the whole part of the system. Justify evaluation by sketching the Nyquist plot for a new system on same Nyquist plot and relate your explanation to stability margins. So when we add integrators into the equation, we will add a constant negative 90. So when it's added, the Nyquist plot rotates clockwise further and move closer to the critical point at negative 1 plus J0. And then when this happens, the gain margin and phase margin will be reduced, while the closed loop will still be stable, but stability is reduced.
For question for A1, he asks you to determine the number of integrator in system 1 and system 2 and justify your answer. So for S1 has 0 integrator because it starts from finite real value, while S2 has 1 integrator start from infinity downward. For question A2, he asks you to determine which system has a good stability. So as you can see, the system 2 obviously have a good stability because system 2 stay farther from negative 1 than system 1. So the first step is we split it as equal to j omega, and then after that we factorize it. So we got 1 over j2 omega plus 3 minus omega squared, and then here with the j we will get 1 over 2 omega plus 3 minus omega squared. That's equation is commutative. So for this we use equation phase equals to tangent negative 1 imaginary over real. So after we substitute imaginary and real, so we got tangent negative 1 2 omega over j negative omega squared. So we substitute omega equals to 0, we will got 1 over j, and the angle is 0. After that we substitute omega with infinity and we got 0, and the angle is negative 180. And after that we rationalize the equation Lj omega by using complex conjugate. Now we will get j negative w squared minus 2j omega over 3 negative omega squared in bracket negative square plus 4 omega squared. And after that we try to find the imaginary part and real part. So for imaginary part we don't get anything, it doesn't exist. For real part we got negative 0.2887j. So for our part it will cross in negative 0.2887, and it will start from negative 100 at 0, and then it will align to negative 0.2887 and stop at 0 degree at 0.1/2. So for the gain margin, you can get 1/8, and the answer is infinity. And for phase margin, you can get from the Nyquist plot, where we will draw a square and you got the base margin in there. So for justification, we can see first on the graph because it is stable as the only cause will exist at omega equals to infinity, and there is no other cause exists. The gain margin is infinite. It's additive system. So for our new GS is 1 over s in open bracket s squared plus 2s plus 3 whole squared. So after we substitute omega to 0, and we will get negative 90, while if we substitute omega into with infinity, we will get negative 270. So we can see that our Nyquist plot is shifted. It's from negative 90 and with negative 270 degree. So by any integrator, we use base margin drastically. Nyquist plot encircle negative 1 once or twice. So the system is not stable. As 0 is a at s close to negative 2. So our new GS is s plus 2 over s squared plus 2s plus 3. As you can see, our Nyquist plot will shift down to negative part, and the system is more stable. 0x especially increase the distance from critical point negative 1 in Nyquist.
That's all from our group. Thank you.